My name is Johan. I've been the project leader here from Solvina. Presenting will be Simon Rolén. He has been the author of this report. So I'll give the word to Simon.
Yeah. Hello, my name is Simon Rolén. I work at Solvina as a power system engineer. And if you don't know Solvina, in the realm of power engineering, Solvina does studies, simulations, modeling, testing, and lecturing. And I will do this presentation for this report called Effective Voltage Control and Operational Coordination of Regional Reactive Power Resources, a case study of western part of the SE3 area. In short, this report is a study which investigates and explains different aspects regarding voltage control and reactive power in the area near Ringhals. And the report has been written by me and by Magnus Lenason, who is now working at Vattenfall. And we have had some help from our colleagues here at Solvina. One of them is Reza Safari. He's here in the chat and will maybe participate if there is any questions later that are in his area of expertise. So I will start by going through shortly the agenda for this presentation. I will start by talking about the aim and the background, so you know a bit why we are doing this report. I will shortly talk about how we did the report in the method section, carried on by, I don't know if the theory is the correct word, but some theory of why we should care about this topic. Then I will carry on by talking about the transmission system side of the topic, carried on with the Ringhals side of the topic. Then I will go through some of the results we have found in the historical data which we have been looking at, followed by some key findings, talking about how it may change in the future, followed by wrapping up about some conclusions, observations, and suggestions. So, the aim of this report is to explain, visualize, and increase the understanding of which aspects influence the voltage and the reactive power in the studied region, and also the interaction between the power plant and the grid. This is with a focus on the area near Ringhals, which we in the report call the west part of SE3 area, and also at the Ringhals itself. Furthermore, the aim is to provide a technical description of the equipment of relevance in the area, summarize demands which the parties need to fulfill, provide an overview of the operational routines and strategies from Svenska Kraftnät and Ringhals, visualize from historical grid data how voltage and power have varied over time, also discuss how future changes may affect the situation. And as I said, this is to give an increased understanding of voltage control in this region. The method we have used is that we started by gathering data. We gather data from Svenska Kraftnät and Ringhals, and the data contain both data for technical components as well as operational routines. We also gathered historical grid data from both Ringhals and Svenska Kraftnät. I will talk about this data a bit later in the presentation. And then we processed the data by summarizing the routines and the technical data. We made visualizations from the historical grid data. In the analysis part, we were focusing on the main aspects that are influencing the situation. We made prediction on future situations and so on. So, why should we care about voltage control and reactive power in the region? Regarding voltage, if the voltage gets too low, we might have stability issues. This is especially true during stressed conditions. And in the worst case, we might have propagating outages. Low voltage may also affect the transmission losses and affect the transmission capacity. High voltage might be negative for equipment. Regarding reactive power, we have mainly been focusing on the effects it has on the generators. So if a generator is absorbing a large amount of reactive power, This might weaken the electromagnetic coupling, which have a negative impact on such as the fault ride-through capacity. And this might lead to an increased chance of the unit disconnecting during faults. And if a unit is producing a high amount of reactive power, this might cause heating problems. So now we'll start talking more about the findings from the report, starting with the transmission system perspective. First, I will talk about the area, then the reactive resources in the area, which demands Svenska kraftnät should fulfill regarding voltage, and lastly, how Svenska kraftnät reacts to voltage issues. Since voltage and reactive power mainly is affected by local conditions, we wanted to limit the area to be studied. And if you can see in the slide here, the stations inside the green lines are included in the study. So we have Gothenburg, of course Ringhals, up to Stenkullen in the north, Breared and Haradsbo in the south, and Tenhult to the east. In this region we have a number of reactive resources, which could be found in the area during the investigated time period for this study. And this time period is from 2015 to 2019. The ones named Kontiskan in this list are located in Lindome to offset the non-linear reactive power consumption of the HVDC Classic link we can find there. And therefore we don't focus much on these resources in the report. There are both mechanically switched shunts and thyristor switch shunts in the area, namely the SVC in Stenkullen. Since the time period which we have studied is up to 2019, the situation isn't the same now. For instance, the SVC has now been decommissioned and will be replaced by a Statcom, also in Stenkullen. So from the demands on the TSO in the transmission system shall be operated between 400 and 415 kV. From the data we could see that the voltage in the area is typically at the higher end of this range. We can also see that on several occasions it has been well above 415. We will look at one of these instances later in the presentation. High voltage is typically more common during low load situations, and vice versa, low voltage during high load. So if we are looking at which actions Svenska kraftnät can take to manipulate or change the voltage, we have this list that we have received from Svenska kraftnät. If I'm not wrong, it's from an appendix to a document called Driftinstruktioner, like operational instructions. And we can see that Svenska kraftnät can disconnect shunts, and these connections or disconnection is always done manually. So it's the operators who gives the command to disconnect or connect shunts. Svenska kraftnät can order an increase or decrease of reactive power to the transmission system. Can also adjust synchronous condensers and SVCs to change the voltage. So that was a bit about the transmission system side of this topic. Now we'll continue with a bit more focus on Ringhals. The time periods, as I said, we studied was up to 2019 in this historical grid data that we have been looking at, and this was before any decommissioning. And here we can see in this list the active and reactive power for each unit. The reactive power for each unit is what the unit is obligated to be able to produce, and this is according to the grid code. And the grid code states that a unit should be able to produce 1/3 of the active power as reactive power. And there is no formal demands or obligations for the units to be able to absorb reactive power. It only states production. According to the grid code, Ringhals must be able to operate continuously at 90 to 105% grid voltage. And if the voltage is slightly outside this range, so 85 to 90, 105 to 110, it should be able to operate for 1 hour with a slightly reduced power production. I think slightly reduced means that it can be up to 10% reduction. And regarding voltage control at Ringhals, the AVRs of all the generators at Ringhals are always in what we call voltage control mode. This means that each generator has a voltage set point value that the AVRs tries to maintain. And the reactive power will then change according to the grid voltage. And the set point for the voltage only changes after a request for change has been received from Svenska Kraftnät. And after change in the set point, the new value remains until a new request is received. Or until the unit, of course, is disconnected, and during synchronization it will receive a new value. And this value will be kept until they hear something from Svenska Kraftnät. So now we will start looking a bit more in the historical data that we have analyzed and visualized. First, measurement data was gathered from Ringhals, where we looked at both voltage levels and reactive power. From this data, we have picked a couple of dates for further investigation, and we picked these dates due to them having either low or high voltage levels, or that we could see that Ringhals was producing or absorbing a lot of reactive power. In this list, we can see the dates that are included in the report. I will only talk briefly about 3 of these dates due to time. So, the data we have used, I want to talk briefly about. For the dates I showed you, data was gathered from Svenska Kraftnät, and this data included voltage levels and active and reactive power flows between the nodes in the area previously shown. This data comes from a program which uses measurement data for where there is measurement data. And if no measurement data for one data point isn't available, the program uses some kind of estimate algorithm to make estimates for these data points. We do not know which values are estimates and which are measurements. And since there are some estimates, there might be inaccuracies in the data. We therefore made a comparison between what I call now estimate data and an additional set of measurement data, just to compare if the accuracy is enough. And in the graph here, we can see the blue line being the measurement data and the orange line being the estimate data. I won't go into too much detail now because it will take too long time, but we can see that the match is decent. And we have said that it's sufficient for the purpose of this report. However, at a few instances, the estimate data deviated greatly from the measurements. And we haven't used these data. So the first visualization I want to show you is for this instance. The main focus for the visualization is to look at reactor control and reactive power exchange between the grid and Ringhals. And I will only talk about some few key points for each occasion. You can read more in the report if you want. So here we can see a situation with high voltage levels in the entire region. In the data, we could see that the voltage was high for a long time prior and after this instance. And we can see that the reactors at Strömma and Kilanda are disconnected, and that these high voltage levels results in Ringhals block or unit 3 having to absorb quite a high value of reactive power. Here we can see a case with high reactive power production from Ringhals. The reactive power production are inside this range of what the units are obligated to be able to produce. So it shouldn't be no problem with the reactive power production. However, this situation indicates that there might be instances where the resources in the area could be used more efficiently. This is since we see that Ringhals is producing a lot of reactive power, and we have all of the reactive resources connected, all of the shunt reactors, and also this SVC in Stenkullen is absorbing reactive power. And I also want to say on this date, we could later, it's not shown in this visualization, but later during the day, when the loading increases even more, the reactors are disconnected. And we can say due to the high loading during this period, but Ringhals still had to produce a high value of reactive power. This might indicate that the Ringhals reactive power production capacity is quite needed during this high load situation. We have seen it in other instances as well. Now I will carry on talking about one of these situations where Ringhals is absorbing a lot of reactive power. And here we can see that it's almost the opposite as the previous slide. Ringhals is importing reactive power with two of these reactors being disconnected. We can see it might have been more efficient if reactors would have been connected instead, especially the one at Strömma that is highlighted in the picture. Some key findings from this data we have looked at is that we can see that the reactive power capacity of Ringhals seems to be used to a fairly high degree, both during low and high load situations. We have seen that the reactors in the area at some instances are connected when it might have been more appropriate to have them disconnected, and vice versa. We have also seen that the SVC at Stenkullen, at the instances we have investigated, is either disconnected or absorbing reactive power. This might not be the most efficient use of the SVC. However, now it's decommissioned, so yeah, the StatCom might change things. And now some of the three main things that we have highlighted in the report that may influence these aspects in the future. The decommissioning of Ringhals 1 and 2 will of course lead to a reduction in reactive power capability in the region. This may be up to 600 megawatts for both Ringhals 1 and 2. The decommissioning will also affect the short circuit power by reducing it. And we have talked a bit more about this short circuit power in the report, but reduction in short circuit power in short makes the area more susceptible to voltage changes. The commissioning of the StatCom at Stenkullen will add about 200 megawatts and will surely be a great resource for these aspects. Also, the commissioning of the Southwest link will aid. The main focus of the link is perhaps active power transmission, but the stations will have a positive impact on the voltage control as well. They will add approximately 300 to 450 megawatts per converter. The stations will surely be of great help in voltage control near the stations, but since the stations isn't that close to Ringhals, it's hard to predict the effect they will have on the proximity to Ringhals. So now I will wrap up with some comments on some points that be of particular interest. and some points that maybe should be looked into more deeply. Starting with the decommissioning of Ringhals 1 and 2, it will, as I said, affect both the capacity and the short circuit power in the region. And with only 2 units in operation, the risk of both being out of operation increases, especially during outage periods. When this happens, it's important that the voltage can be controlled without the aid of Ringhals. It should also be noted that it is of importance for Ringhals that the voltage in the transmission system is inside this acceptable range, even when all units are connected. This is from a nuclear safety perspective. And it can be seen in the data that on some instances, the reactive resources may not have been used in the most optimal way. If the case is so that without Ringhals in the future, the system is a bit more fragile in terms of voltage control, the control and the routines for operating the resources maybe can be improved. I haven't said anything about this previously, but maybe I should mention it. And it's that distribution grid historically have been injecting reactive power above the levels they should in the region, which makes the voltage a bit harder to control. This might also be something to look into in the future. Regarding reactive power capability, as I said, the decommissioning will be followed by a reduction in capacity in the region. The STATCOM and the Southwest link will add capacity, but maybe it could be of interest to study this to a greater detail, since we could see in the historical grid data that the reactive power capability of Ringhals is used to a fairly high degree. On the topic of voltage control, apart from the capacity, the voltage control and the voltage stability in the area may need to be studied more in detail as well. It's quite hard to make predictions on this topic, since there will be changes in power flow, changes in short circuit power, and new equipment will be installed. So it's a hard topic to make predictions on. And finally, the communication between Ringhals and Svenska kraftnät could potentially have room for improvement. This is since, as I said, the set point for the generators are only changed after Svenska kraftnät asked Ringhals to change the set points, and this doesn't happen very often. And that was about it for this presentation. I think it's a quite interesting topic. It's hard to make predictions, and it's of high relevance, as we could see this summer with the Ringhals 1 being, I don't say forced, but taken into production due to short circuit power and voltage stability. And I would like to thank Svenska kraftnät and Ringhals for the help they have given us in this report, and all other participants in the project, and special thanks to Monica. That's it from me.
Thank you very much, Simon. Would anyone else in the project team like to comment something?
I just want to say something. I'm Reza from Solvina. So it's mainly about Robert comment, which said about the droop of voltage control. Because as Simon said, since this project was mainly about in sort of, let's say, load flow level and static analysis, so we haven't gone through the dynamics and details of the voltage control, and that's why Simon also said that for further like prediction we need more detailed analysis. So at this moment, at least I don't know that is there any like droop control for generator units in Ringhals. So my point was we haven't gone through there, but as there are or used to be 4 units in parallel, so it makes sense to have some sort of droop, and maybe deadband or not. So we don't know at this moment. At least I don't know. Maybe Simon, if you know about droop control for the units in the Ringhals, maybe you can add something. But so because
I don't have it right now. Maybe we can.
Yeah. Because I mean we haven't gone through there because it was more like detailed sort of voltage, like dynamic stability and so on. So, but we focus mainly on the load flow and the static part of the problem.
Would anyone at Ringhals like to comment? Yes, Magnus, you raised your hand. Magnus Knutsson at Ringhals.
Yes, Magnus Knutsson, Ringhals here. I can comment on the question. We have no deadband in the AVR, and we have no droop as well. So
yeah, thank you.
We keep the voltage fixed.
Yeah.
At all times. Thanks.
Thank you.
And there's a question from Jonas Persson at Vattenfall. Jonas, please. Remember to unmute, Jonas.
Yes, do you hear me?
Yes, we can hear you.
Yes, I just wonder if you can have seen any worse voltage quality during revisions of the Ringhals generators. Is the voltage quality less during summer, for instance?
During summers, I think it's mainly due to the loading situation, but we haven't looked specifically during the revision periods. So unfortunately, I can't say if it's specifically worse during revisions than during our summer, like the summer period.
Yeah.
Okay, thank you.
Thank you. And do raise your hand or write questions in the chat. I have a question, and that is, you mentioned that some of these measures to control the reactive power are made manually. Would it be better with some kind of automatic control, or is that not possible? Or
sorry, can you repeat the question?
You mentioned in your slide that some of these measures that can be taken from Svenska kraftnät to adjust, they are taken manually by the operators. Would it be better if that was made automatically?
Maybe, I think.
Maybe I can comment. I mean, since, as you know, Monica, this industry is very conservative, the power system. So maybe that's why they go for like the most sort of like safe and then go for manually. But in the sense of, from my point of view, so if we have sort of automatic, definitely would help. But the point is, some automatics are making the system more complex, as it is already complex system. So it's sort of trade-off, because I mean, in some cases, for example, especially during the maybe restoration, at least I did experience that in some cases they go mainly for just manual, but we need like a speedy sort of restoration for the system. So having the automatic is definitely help, but I believe that since the industry is very conservative, so and also we need to take care of, if we add automatics, how much we add complexity to the system. But in case of like voltage control automatics and some sort of maybe droop and so on, so maybe that's not the problem. But I think we should be careful about both adding not further complexity to the system, which is already very complex, and but at the same time, adding automation to the system helps.
Thank you, Reza. And a follow-up question: if we would use the system optimally, would it be like no need for further investments then, or how much can we sort of save if we would use the system optimally?
Honestly, I didn't get what the question is.
If I understand correctly, the study has shown that in some cases Ringhals and the grid are sort of counteracting each other. But if we would be able to control this system better, so that both the nuclear power plant and the grid would work sort of optimally.
Oh, you mean, is there any like a space, or I don't know? Because I mean, what we understood, at least from this report, was definitely there are some like, what is called? Some sort of work need to be done further, because in some cases, as Simon showed, that we had like not very good coordination between Svenska kraftnät and Ringhals. For example, sometimes the voltage, the ring holes are absorbing reactive power, while there were some not connected reactors in the system. So definitely there are opportunity that we can take them as like more coordination between Svensk Kraftnät and Ringhals to get more optimal output. Yeah, there are.
Yeah, I think as your question was also if we just improve this coordination, we don't need to make that great further investment. Monica, right?
Yes.
I think that is a topic which our report didn't go into details of this that much, but I think it's a topic that should be investigated. It's quite hard to make predictions about this because, as I said, it's complex, but my prediction is that just better coordination might not be the solution that can fix everything, but it sure maybe can decrease need for further investigations. But I don't think we can say if it's to which degree.
I understand, and I know that was not included in the study.
No.
So we have a question from Mattias Karlsson at SSM. Mattias, please.
Okay, yes, I'll try to explain. The question is regarding if it's possible to quantify the value of the voltage control devices that we have. I mean, we have a number of, or you have a number of devices in the study that are providing possibilities to voltage control. And can you say something about the relative contribution to voltage stability from each device?
I think we have some small comments about this in the report, but to quantify it, maybe it's hard, but it can maybe be done in a further study. But of course, like regarding voltage control, it's I think the StatCom and the HVDC link are, of course, quantity-wise quite good, but like mechanically switched shunts are a bit harder to, like if you were to quantify the value regarding voltage control, that quantity would of course be lower, but I think now so that, yeah, that's about what I can say about that. It's also something that maybe could be of interest to study more.
Thanks.
Thank you. And another question from Jonas Persson. There you go, Jonas.
Yes, hello. Can you hear me?
Yes.
Yeah.
Very good. So I just wondered, would it be better to change the AVRs more often, and how often are they changed today? You said it was by a signal from SVK. How often is that done, the plants?
I don't know exactly how often, but as I understand it, it's not very often. Maybe a couple of times per year only. But if it's beneficial to change it more often, like from a voltage control perspective in the region, I would think that it could be more beneficial. But then you would need to study like what are the pros and cons of changing it more often. So it would need to be a study which like looks more thoroughly in like the Ringhals operational, how they operate, and also Ringhals. So it's one thing that we have seen as a potential also study in the future. It feels like I repeat myself, but as I said, this like report has been to highlight some of these interesting topics. So we don't know for sure, but it has surely the potential.
Yeah, and also to add something to this, Simon said, maybe, yeah, as Simon said, that we need further study, but something that is a bit maybe, yeah, we can think of it is because when a Svensk Kraftnät like ask Ringhals to change the set point of the voltage, so they do change, but when the situation gets better, still they keep the set point that already been asked by the Svensk Kraftnät when the situation was not the same as it is now, for example. So maybe, I mean, keeping that set point for a long time when the problem is solved may be something that need to be think of that.